Bonjour à tout le monde. Donc mon nom est Bernard Billat et je serai aujourd'hui le modérateur de ce webinaire. Donc ce webinaire consiste en une session de questions-réponses, questions que vous nous avez posées, qui ont été sélectionnées par notre comité d'experts. Donc je souhaite la bienvenue à tous ceux qui sont déjà présents. Nous allons attendre quelques minutes de plus que tout le monde puisse éventuellement se joindre à nous. Donc j'en profite pour donc déjà vous remercier d'être présent pour les personnes déjà présentes et également pour vous transférer quelques informations qui peuvent être utiles pendant le déroulé de cette présentation. Donc vous avez la possibilité de poser des questions. Donc vous avez dans votre panneau de contrôle un onglet questions et donc vous pouvez écrire vos questions. Donc nous allons prendre les questions par écrit et nous allons essayer d'y répondre à la fin du webinaire. Donc si nous n'avons pas le temps de répondre par oral, par écrit, par oral à ces questions, ne vous inquiétez pas, nous répondrons à toutes les questions et nous enverrons notre réponse à ce moment-là par un courrier électronique. Deuxième information importante, si vous rencontrez des difficultés avec le son ou avec le visuel de la présentation, donc n'hésitez pas également à nous le signaler. Donc vous avez pour ça un onglet lever la main et on fera le maximum pour essayer de rétablir le son ou le visuel. Et donc ensuite, une dernière information, on a préparé pour vous aujourd'hui quelques documents qui sont disponibles dans l'onglet Handout et vous pouvez donc télécharger, consulter et télécharger ces documents. Donc ce sont des présentations, ce sont des notes d'application qui sont en rapport avec la présentation d'aujourd'hui et donc qui peuvent être très utiles. Donc, je pense qu'on va maintenant démarrer la présentation des différentes personnes de notre comité d'experts. Donc, vous avez le docteur Frank Panoffen, qui est notre directeur et le general manager de la division Life Science de PMS. Donc, Frank est basé en Allemagne et donc répondra à une ou plusieurs de vos questions. Nous avons ensuite Mark Allworth. Donc, Mark est basé aux États-Unis, à Boulder, à la maison mère de PMS. Marc est notre spécialiste, notre grand spécialiste de tout ce qui est question GMP et un scientifique expérimenté. Nous avons ensuite Daniele Pandolfi. Donc Daniele est notre Global Production Line Manager pour tout ce qui est système de monitoring et logiciel et services. Et moi-même, donc Bernard Billat, qui suis le responsable de l'agence de la filiale PMS France et Benelux. Avant de démarrer, je vais juste vous donner quelques informations sur la société PMS, donc Particle Measuring System. Donc Particle Measuring System est une société américaine. Notre cœur de métier, c'est tout ce qui est assurance stérilité. Donc dans ce but-là, on a différentes compétences. Donc la première, c'est tout ce qui est équipement de mesure. Donc on peut effectivement fabriquer et proposer des compteurs de particules, biocollecteurs. Ensuite, on a également la possibilité de proposer tout ce qui est logiciel, donc logiciel de monitoring, logiciel également pour aller avec les compteurs de particules, etc. Un troisième volet, c'est tout ce qui est expertise. Donc, on est en mesure de vous aider avec notre équipe d'experts à, par exemple, préparer un audit. On peut également vous aider à préparer un monitoring, tout ce qui est également levé d'un commentaire qui a pu être fait par un auditeur. Donc, nous avons un comité d'experts qui est prêt à vous aider là-dessus. Également, tout ce qui est analyse de risque pour définir un logiciel pour définir une stratégie de monitoring, par exemple. Et enfin, on a tout ce qui est service, formation, donc tout ce qui est calibration des compteurs de particules, bien sûr, des biocollecteurs, tout ce qui est également le service pour les systèmes de monitoring et la formation. Nous avons également ce qu'on appelle les Particle College. On fait des webinaires, on fait partie également de tous ces organismes de formation. Voilà, on va passer à la première question. Donc, ces présentations-là vont avoir lieu en anglais, en langue anglaise, hein, comme c'était convenu. Donc là aussi, si vous avez des questions, des points que vous n'avez pas très bien compris, très bien saisis, n'hésitez pas à poser ces questions-là par écrit et on essaiera d'y répondre au mieux. Donc la question numéro 1, quels sont les changements majeurs dans la nouvelle annexe 1 des BPF? What are the major changes in the new Annex 1 of GMP? Donc la présentation va être faite par notre expert Daniele Pandolfi, qui va donc vous présenter ce premier sujet. Daniele, that's your turn. Are you ready?
Thank you, Bernard. Welcome, everyone, and thank you very much, Bernard, for your introduction. So let's jump immediately into one of the hottest topic of this season, the upcoming release of the new GMP Annex 1. Before going into the details of some overview of what has been changed or is going to be changed in this new revision, I would like to focus your attention on the reason that brings the committee, the GMP committee, in evaluating the change and the revision of this important standard. First of all, it has been made clear, extremely clear, the importance of the principle of a quality risk management. And also the GMP Annex 1 is putting a strong focus on the needs of really use the current technology, the updated instrumentation, technology, machinery, to really bring the pharmaceutical production up to date with the current standard. Together with that, there is another important aspect, which is which is encouraging the use of single-use and closed system as well as disposable system. And last but not least, is the needs of defining a contamination control strategy. This is a frequently used term and really can be summarized in the word understanding. Creating a contamination control strategy means understand your facility, understand your equipment, understand the process, and make the data become information to make update, to make change based on the feedback that you can collect from the data you are receiving from all your instrumentation and your monitoring device. Next, please. The clean room classification and qualification versus monitoring. This is one of the most important change that I would like to underline. The GMP is making now clearly the difference between the classification, qualification, and the monitoring. And this can be really summarized in one sentence. Do not use classification limit for monitoring. Everybody knows the standard table of particle limits that are used for classification. So when talking about monitoring, these numbers should not be used. They, of course, represent the highest limit, of course, but your monitoring alert and action level, and we will see it later, should be based on historical data, should be based on your increased knowledge of the clean room performance. Next, please. Another change that we show now, here we go, in the next slide, is the removal of the 5 micron particle equal or greater than 5 micron from the clean room classification. This is reflecting what the ISO 14644-1 introduced in 2015. Because of several limitations, one of the most important is the particle loss that can happen in the tubing makes the classification at that particle size and for this low number not adequate, not applicable. And also it emphasized the GMP Annex 1 new draft, emphasized the need to set up again alert limit based on risk and historical data. So this would be certainly an important change. In the monitoring, as you can read in this comment, still the 5 micron are considered to be important, to be controlled, but not in the classification and qualification where they will be removed for the grade A of the clean room. Next, please. So we mentioned about alert and action level, but how they should be really configured. First of all, let's describe a little bit the difference between these two terminology. An action limit is an established relevant measure that when exceeded should trigger investigation, corrective action, and to find the root cause of this specific alert action exceed. The alert level instead should be considered as an early warning of a potential drift from normal operation. In other words, the alert should be properly set up to inform the user, the people in the clean room, in advance that something may go wrong shortly if no corrective action are taken in an immediate time. So both of these should be based on trend and should be also based on a specific alarm and action strategy. Next, please. So how do I set up my limits if my clean room is new? This is a frequently asked question. How can I do that if I don't have historical data? So you should start based on the clean room classification information. Then collect the data for a period of time, which is typically 4 to 6 months, analyze your trend, evaluate your trend, and then define your new alert and action level. It is important, again, to start from the classification data and not from the classification limits, because your classification data will certainly be better than the classification table maximum limit. Another important aspect in this slide is how to choose the right strategy. Can you just click once, Bernard, please? There's text that will, no, go next. Here you go. So, go back, please. Okay. The right determination of alert and action level should be based as well on strategy and should be based on a continuous evaluation, because your trend, your process, your activities in clean room may change over time, and a risk assessment should always support the decision you are taking. Next slide, please. The ISO 14644-2, for example, to which the GMP Annex 1 refers in several points, states the importance of a long-term evaluation, as well as an yearly, at least yearly, reevaluation of the method, frequency, and limits. Perhaps this will not be necessary to change your limit year over year, but at least you should question yourself whether the existing monitoring plan is still applicable, is still appropriate for the specific intended use. Next, please. I'm referring again in this slide to the ISO 14644-2 because it introduced a very important paragraph, the B313, that talks about how to define an appropriate strategy of alarm. This specifically describe how nuisance alarm, so alarm that are triggered too frequently without reason, can lead user to not consider that, to disregard that. So the ISO provide a couple of examples of the strategy that I want to show you in the next slide, please, that will make this topic much clearer. The strategy 1 established a trigger threshold value based on a series of consecutive high readings. In this example, 3 consecutive readings of 1 minute sample will trigger an alarm. As you can see, this red line shows the alarm level. The event number 4 in the bar chart is not considered an alarm, as well as the event number 12, but the combination of 3 consecutive exceeding, these generate an alarm. In other words, you can set up your strategy based on 3 consecutive, 5 consecutive. You can define based on your risk evaluation, but it should not be based on a single event triggering alarm. The next slide shows another example of strategy provided by the ISO that is applicable for GMP, that shows the techniques called X out of Y. In example, 3 sample out of the last 10 readings as a moving windows. So again, in this example, these 3 readings in a 10 minutes windows are considered then alarm that trigger an action for the system. So these are just some of the highlights of the upcoming UGMP Annex 1, in particular for the particle contamination, for the non-viable contamination. Of course, there are a number of changes around the microbial and around the facilities and other aspects. One important point to keep in mind, and I invite you to make this comparison, is checking how many times the GMP is now mentioning about quality risk compared with the older standard, and you will certainly understand how important this will be in your life pretty soon. Thank you, Bernard. You can go to the next question.
Yeah, so thank you, Daniele. Thank you so much for this presentation. So there is no question for now. So let's go to the question number 2. What are major sources of greater than 5 micron size particle? What particle size channels give the best estimate of fungal contamination? And for the setup of the total aerosol particles for in-process, how are excursion handled due to tubing and spraying of ends? So Mark will answer these questions and provide you the information. Is Mark there?
Yeah, Mark had some difficulties. He is in now, but still we are not able to unmute him as he's
Okay,
not
so
attending.
let's go to question number 3. And
wait a second. Mark, can you try to unmute yourself? You should hear me.
Mark, can you hear us?
I think I'm in.
Okay, yes, you
Mark,
are. Okay.
Welcome in this presentation. So
Thanks very much.
in time. Thank you.
I was having a panic moment this morning. All right.
No problem.
So the 5 micron sort of takes on its own entity in how we look at Annex 1 and how we look at these environments. It's most of the emphasis that's being placed on changes within monitoring is around the 5 micron, and therefore there's a lot of concerns about them. Now, if we start to look at the major sources of particles in a clean room, where are our particles coming from? Well, as we all know, the greatest source of particles in a clean room are our operators, because a well-designed clean room pretty much generates no particles at rest. Even Class C and D areas, once you've taken all the people out, the process noise itself is relatively low. And those large particles tend to be associated with skin operators, clearly, skin flakes, so exposed skin, where that might come, or even skin that migrates through gowns. And gowns are essentially filters. So the tighter the weave on the filter, the more the operator sweats, the more uncomfortable they become, the more they move about. That releases both skin and fibers into the air. And fibers typically show up in that 3 to 5 micron bin. So if you're monitoring a clean room and you see 3 to 5, and as we know, 2 3s in the laser at one time looks like a 5. So you can get this like an escalation of small particles that look like large particles. Water vapor, if you open an autoclave, the vapor in air will look just like a particle. The particle counters are relatively inert beings, and they don't differentiate between water, particles, microbials. They are total particle counters, which is why some of the language has changed here too. IPA sprays, if you're spraying IPA in the corner of a room and you see a spike in the other corner, remember your ISO 7 clean rooms are turbulent flow. They're designed to mix air to an acceptable level, and that mixing can yield random 5 micron, random large particle events in places where you weren't anticipating them. And then finally, cleaning residues, which is why Annex 1 spoke quite specifically around the occasional indication of a macro particle count, especially greater than 5 micron, may be considered a false count due to electronic noise, stray light coincidence, that's the 2 particles simultaneously, etc. And so one shouldn't always be overly reactive to a single event of 5 micron particles. As we can see, people, the largest 70% of particles within a clean room come from operators. This was from Thomas Barber's book, Control of Particulate Matter Contamination in Healthcare Manufacturing. Process, materials and facilities account for the other 30%, whereas process, we're starting to look at belts, friction, movement, lubricants. Vibration is a weird one because that can cause sedimentation releases of particles in transport tubing. So if you look at the next slide, Bernard. So the question also asked around, so we're aware of where the particles are coming from and that their bias is towards operators and large particles. Fungal contamination is typically a demonstration that the clean room is out of control, as opposed to it's being tied to a specific process. Or so fungal contamination, mold and spores tend to come from a general lack of a cleanliness program. As we all know, the beginnings of a good environmental monitoring program begins with a good cleaning program, cleaning and sanitization program. So if you are starting to see an increase of fungal spores, the particle counter will basically show you an elevation across all the size thresholds. You'll see increased particles in the smaller sizes as well as the larger sizes. So there's nothing unique about fungal spore or fungal and mold contamination per se within a clean room. You're looking at a total environmental control concern, as opposed to I have to look at my people, or I have to look at gowning or gloves or face masks or anything in particular. It tends to be, you know, this rising tide of lack of cleanliness. Next. And as Daniele was saying earlier, this is actual data from a clean room. And I think if you just press the next button just once, Bernard, you'll see that red thing slide. That slides in the wrong place. It's meant to show you that the occasional cluster that we see early on in that plot, you've got occasional counts. Now, occasional counts, random events may well happen, but in the center there, a little bit to the left of where the red slider is currently, there's a cluster. And it's those clusters that we're looking for. So again, the occasional indication of a macro count can be false counts due to electronic noise, stray light coincidence. However, this 922 continues, and this is in the old Annex 1 under Note 13, paragraph 13. It's in the new one under 922. Consecutive or regular counting at a low level. maybe indicative of a contamination event. So now we have to start determining what is consecutive or what is regular. So what they're not looking for is routine. So a definition tends to be more time-based than magnitude. We're not looking at, and how big a magnitude does it say? Well, such events, consecutive or regular counting of low levels. So we start to look for, well, what does a low level mean? So we've got two variables here. One is over what time does it look wrong? And two is of what magnitude? Because certainly 1 or 20 or 35 is not the number. It should be in line with what your process is telling you within that facility. I've seen plenty of companies throw product away because of a single 5 micron event, assuming that that single 5 micron is a loss of control over the environment when it could have been a natural incidence of 2-3 micron particles being generated by a friction on a conveyor or glassware rubbing together that cause particles in the air simultaneously. So it has to be tied to what would be deemed a contamination event. So IPA sprays are right there. If your operators are spraying IPA as a cleaning exercise, then it really shouldn't be whilst product is exposed to that air. IPA spray is not sterile. It can be provided sterile, but as we know, bacteria and spores can grow within an IPA environment. So you can't consider IPA spray to be a sterile liquid, and therefore any cloths or sprays are a potential contamination source. Next. The second factor that comes into monitoring 5 microns is particle dropout in transport tubing. So the particle mechanics of transporting particles from the point of measurement to the sensor itself is quite critical. Right now, there's a lot of confusion around the actual length of tubing that can be used for monitoring. There's a recommended length for certification if you're using a particle counter for macro particles. That's ISO 14644 Part 1, and it's Appendix C. Talks about sampling macro particles, and it recommends a greater of no more than 1 meter. But in our environments, we're not looking at uniquely 5 micron and above events. We've got 0.5 and 5 to consider. And as such, we recommend no more than 2 meters of tubing, because although you will see, in the order of 20%, 25% losses in transport tubing of that 5 micron, you've got a corresponding smaller loss of 0.5 micron that allows you to manage the process based upon a data stream, not a unique single measurement. If you're taking unique singular measurements, and that's got to do you for the day, the week, the month, then certainly the shorter the tubing length, the better, because that's a single point where its measurement must be more absolute, because you're going to rely on that data to demonstrate the room's cleanliness. Whereas in monitoring, what we're doing is we're looking at the room, assuming it to be clean because we've got this continuous stream telling us so, and we're now looking for anomalies to the norm. Next. So particle loss considerations. Particle losses do increase as particle size increases, so we won't see very many losses at 0.5, but we will see large ones at 5. The higher the Reynolds number, and there are plenty of resources out there on our website where we can download for free application notes that we've written, and I know I've contributed to many of those over the years, that talk about particle dropout and transport tubing. And our recommendation is 2 meters. If you can get away with 1.7 meters, use 1.7. If 1 meter is the right length, then you don't need 2 meters, use 1 meter. The longer the length of tubing, the greater the sedimentation rate, so the shorter the better. But 2 meters would be a recommended maximum. If you need to exceed that, then simply perform validation exercises showing particle loss in that transport tube. And a recommendation from us wouldn't be to try to amplify results based upon the losses, but to reduce the alert and action levels based upon the losses. So if you have a 10% loss of 5 microns, then reduce your alert and action levels by 10%. Next. And then the importance of isokinetic sampling probes. In general, ISO 7 and 8 areas, isokinetic probes are merely there, or really there as a means to make the particle counter look right. Where they're critical is in unidirectional flow conditions, or first air as it's now being called. So the air coming straight off the face of the filter should be flowing along axial lines. And so we've got two issues here: isoaxial, that is that it points into the face of the filter, and isokinetic. Isokinetic means that the sample rate as it enters the sample nozzle is at the same speed as the airflow that's passing the nozzle. So in the first instance, we see parallel lines. That means we're taking a clean sample where we would get a 100% correlation with the particles in the air versus the particles in the sample. In the other two examples, what we will see here is an over or under sampling of the large particles and the small particles in air, and that would shift the curve of the particles in that distributed sample. The same if you start to move isoaxial. So if you're pointing directly into the plane, then you'll get 100%. If you start to point at 45 degrees, you're now going to take what will look like an elliptical sample from that environment, and thus create an isokinetic error. So sampling, we've got to point into the plane and sample at the right rate relative to the airflow coming into it. There's quite a bit of error allowed on the size of the probe. It's actually quite amazing how wrong a size probe. So we've got 0.45 meters per second face velocity plus or minus 20%. You've got almost that same latitude of tolerance on the sample probe inlet. So if you have any questions, please feel free to reach out and ask around any specifics. But for the most part, providing that you're using the isokinetic probe provided with the instrument and it's pointing into the flow, we should all be okay. Next.
So thank you, Mark, for this brilliant and clear presentation. So we go now to question number 3. So how to define the frequency of sampling? Why is continuous monitoring essential for containment? Do the regulation require continuous environmental monitoring? In which cases a continuous microbiological monitoring can be relevant? And this will be answered by our German expert, Frank Panoffen. Frank, it's you.
Yes, hello, thanks a lot for introducing the question. So it is all about sample frequencies and how often do you sample, and of course continuous monitoring is, let's say, the ultimate final stage of high frequency. So the higher the frequency, the closer you come to the continuous monitoring. I have some difficulties. Just a second. Okay. Just a second. Okay, good. Now I'm good. So the easy answer, or the simple answer, is how to define sample frequencies and how to define whether something needs to be sampled continuously or not is, in the end, nowadays, quality risk management. This means in the Annex 1, you see that quality risk management is the state of the art of determining any type of methodologies, frequencies, parameters, and so on. If you do not have a good risk assessment and understanding of the process, you will not be able to define it, and the auditors will expect that you have such written evidence in your hands. Now, from now on, already it should have been already since some years ago, we will never accept anybody saying, listen, I did it all my life this way and it worked all my life and my products were sterile. This is no longer something that is acceptable from an audit perspective. You must have written, documented evidence, and this is the scientific justification. It must include the scientific justification why you're doing that. Next slide, please. So again, the risk assessments are used to establish the environmental monitoring program. And there is multiple factors. One is the detailed knowledge of the process. That means you really need to know what is happening within your process, and you need to do a Gemba walk if it's needed. You need to review your historical data, which is another very important aspect. And you need to understand, for example, from a microbiological perspective, what is your typical microbial flora. So knowing all the parameters that you would be expecting in your environment is vital and is paramount for deciding the which factors go into quality risk assessment. They are living documents and must be part of the now called, and Daniela had already introduced the concept of the contamination control system. The contamination control system becomes the overarching documented evidence that you have done everything in best faith and with best scientific knowledge to prevent contamination to occur in the final product. Next slide, please. Looking into the aspect of the viable sampling and the sample frequencies from the viable perspective. The first thing is, in the Annex 1, it is written that monitoring, microbial monitoring, must be frequent. Frequent means not just one time. That's the first thing. You cannot say I did it one time and that is frequent. So minimum is that you can understand and you understand that you monitor as frequently as it is needed to build the full process around and to monitor the full process and as well capture all different incidences and so on. Again, the same is according to the methodology. You cannot go away and just say, I do now viable air sampling because I do it all the time. No, you must understand the methodology, for example, of viable air sampling, and you need to show in a justification, in a scientific justification, which is why you have chosen the method, which data it will generate, and how you are going to handle this data. Continuous viable air monitoring has become, let's say, the running requirements, knowing that for particles in grade A zones, we do have already the continuous viable air continuous particle monitoring since 2008 in the Annex 1. So continuity and continuous sampling is something that is the best to monitor and understand the quality of your environment. For air monitoring, this was in microbiology, this was for a long time something that was not even possible. So what has been done in order to replace air monitoring in a continuous way, the people were using saddle plates. But we need to understand, and I come to that in a few moments later, saddle plates are not a measure of air quality, and it's not monitoring the air. No, it is monitoring the settling frequency of particles that have viable aspects. So you are measuring the surface particle contamination rate. It is not an air monitoring that you're doing. So knowing that now we have continuous viable air monitoring as a potential requirement in the new regulation, we need to think about other measures and how could we reach and come close to the continuity of the process. That means traditional viable air monitoring, for example, with longer sampling time is one option. The other option would be rapid technologies like laser-induced fluorescence, which are now becoming more and more popular. Next slide, please. And this is just a summary on continuous viable monitoring, because I really love this graph. In this graph, you can see down on the bottom what would happen if you use a 100 liter per minute sampling viable air monitoring sampling device on an 8-hour manufacturing time. If you just sample once, you would only have 1 cubic meter sampled, and it would not even meet and not even capture contaminations that would have been done by an intervention, for example, that you see happening here. If you increase the sampling times by slowing down the sampling flow, you get more and more data and more understanding of the whole process. This is why we are promoting, and we are a strong promoter of the fact that using 25 liter per minute is the best way of getting a good efficiency in sampling of a viable air monitoring sample. But on the other hand, you are already starting to get a big overview of the continuous process and the continuous manufacturing that is running. In the extreme, and this is what people are doing nowadays, more and more, is if you use a single use device like the BioCup single use on the upper right corner, qualified for 2 hours or more sampling times, you can build up on a process of 8 hours with 4 devices and 4 sampling times, and you have a continuous monitoring of the whole process. Remember, and I told you already, settling plates are not air monitoring devices. Settling plates are measuring the surface contamination rate and not the quality of air. The other additional thing is, be aware that settle plates have a very difficult methodology because they cannot be validated. If they cannot be validated, you are not sure how to handle them within your contamination control strategy and how to build up consequences out of their results. So you will have difficulties and you have no chance even to quantitate your results and to say this is acceptable, this is not acceptable. So saddle plates in clean rooms, and I'm talking about class A only, I must say are an ancient relict of microbiology, and there is other methodologies available that can be more precise and can deliver a continuous monitoring of the process. Next slide, please. So how to do the risk, the environmental monitoring risk analysis? I would like to give you a very brief introduction into how we in our organization are promoting these kind of technologies. And please, next slide. And next, please. Without the risk assessment, you will have poor or wrong definition of the methodology. You have either too few or too many sampling points. You will not have data correlated to the process, and the positioning of the particle counters or the viable samplers are not well defined and well designed. They may be prone to false positives and so on and so forth. Heights are not defined, so without it, it is really difficult. And of course, the frequency of sampling is not defined as well from a pure scientific perspective here. So next slide, please. Yeah, next one, please. If you do it in the correct and right way, how we are doing it in a guided process, you first start with the first step in understanding the processes, and you define by an HACCP the critical areas. You evaluate then all the sampling methods that are possible, and afterwards you define the sampling points. So that the second step is, you see, the second step is that you have now defined the critical control points. You have some areas where you do not find critical control point. The third step is, if you now click on next, that the methodologies are defined for these control points in order to understand which data you want to generate and which data is relevant for these critical control points. In the fourth step, you then define the right, let me say, the right way. You define clearly what are the potential sampling points, what space you need, what are the requirements there, what are the interferences from the surrounding, from material, from the personal flows, and so on. So you then know this, and in the fifth step, with an FMEA, you then really understand and define the representativity, the design of the sampling, and understand as well the criticality in a way that you are having exposure to primary containers, for example. And this together defines the sample frequency, the incubation condition, and so on. And you have a risk mitigation strategy defined with the total concept of this EMRR, environmental monitoring risk assessment solution. Next one, please. So conclusion is, following the method of risk assessment under a contamination control strategy, you will have the chance to understand the right methodologies, the right sampling sites, and the right frequencies, which can even lead, in best cases and in understanding, in the reduction of sampling sites, and as well in the selection of the right locations. And when you use the right methodologies in extremes and in essence, you can really additionally go towards a continuous monitoring of microbiological air control. So I think that was the last slide, and I would hand over to Mark.
All right, so thank you very much, Frank, for this for answering these very important questions. We are now going to question number 4. So what good practice are recommended for the microbiological control of medical gases? What, how, and frequency? And this question will be answered by our specialist, Mark Allworth.
Thanks, Bernard. The hard part here, and probably the reason why the question was asked, was there isn't. This one says there is a lack of specific guidelines, regulations for pharmaceutical applications for compressed gases, and therefore it's kind of what we tried to do is search out what regulatory or standard advice is out there and try and jam them into the problem. So we could have a look at both the ISO standard and the FDA, and the key attributes for compressed gas are solid particles, water, oil, and microbiological burden. If you go to the next slide. The FDA have a requirement that a compressed gas should be of a quality appropriate to purity, i.e. that it should be equal to or better than the air of the environment in which it's going to be used. So if you're using it as an overlay gas, that's critical contact, that's grade A, it should meet at least grade A requirements. That is less than X number of particles and 0 less than 1 CFU. So if you're using it as a conveying mechanism, then again, if it's conveying solid dose and your solid dose tableting mill runs at an ISO 7 environment minus the product, obviously we can't do it whilst there's powder around, then that should be the quality of the air that you're measuring. So it's how are you going to use the compressed gases? Next. ISO 8573 is often referred to because it's the only one out there, and it has 9 parts. The interesting ones for us: containments and purity classes. It's always good to say my gas is a class X gas. And then part 7, the test method for viable microbiological contaminant content. So if we look at first part 1, next. this gives us the ISO compressed gas classes. Now, immediate to note is that what we're really looking at here is all of the gases that we'll use in our facilities are essentially class 0, i.e. as specified by the user or the supplier, and they're certainly more stringent than class 1. Class 1 allows for 20,000 particles per cubic meter at 0.5 micron, which would be, you know, an unacceptable limit, maybe ISO 7 at a squeeze, but the reality is that we have to set our own standard classes, which we're allowed. We call them all class 0. Next. So what does class 0 mean? Well, in pharmaceutical production environments, we therefore associate a class 0 as per ISO 8573 part 7 or part 1, sorry, as the equivalent for grade A or ISO 514644 part 1. So we have to try first off is to relate the two standards together, which allows us to, you know, describe in our documentation that this compressed gas test, it should meet this standard. Next. So part 7 provides a means of sampling, incubating, and determining the number of microbiological particles. It focused on slit to agar. Now, there's very few, if any, instruments out there that are able to do compressed gases using slit to agar. So what industry have done as a standard, slit to agar is essentially an impaction mechanism. So we've chosen an impaction tool to take that sample. If the standard says that you first depressurize the gas and then take the sample. Now in the Minicap Mobile, what we've got here is right on the top, there is a compressed gas coming in. There's a pressure regulator that allows for the depressurization of the gas, which then goes through into a diffusion chamber that allows the gas to expand at a 1 atmosphere rate, and it's then drawn through the impaction plane and onto the agar. Any excess flow, so a breather if you will, is allowed to vent into the open via a filtered exhaust. Now that filtered exhaust, let's for instance say during setup you're not quite supplying sufficient gas and it's undersampling, then clean air will be drawn in through the filter and therefore sampled. So it's almost a safety check valve, having that filter there for both exhausting compressed gases into an environment, but also should you be doing this in a technical space, you've got the assurances that you're not going to be sampling the environment, the technical space environment, relative to the microbial burden at the test point that you're using for the compressed gases. So it's quite key that this depressurization, that's what ISO is asking for, that depressurization occurs prior to. Now there is, you know, certain concerns around the depressurization damaging microbes. There's certainly information around that shows that doesn't happen to any significant degree, and so depressurization and then sampling is the norm, and that allows for standard equipment to be used. For instance, this equipment uses a compressed gas accessory, and ordinarily it's being used in the day-to-day environmental monitoring of the cleanroom locations. Next. So what sort of frequencies should I be using for my compressed gases? Well, again, that ties back to the FMEA. Is it, you know, 1 weekly sample or 1 monthly sample? If it's my grade A environments where I'm using this as a critical overlay, then that should be more regular relative to the concerns that it poses there. So qualification should be performed routinely, and at which location? Initially, every single sample should be done, every single tapping point should be done. But after that, we should be looking for the end of train or immediately prior to use. So if there's a final filter prior to use, that's the point at which we should be taking our samples. Next.
And we are done. So thank you again, Mark, for this very clear presentation.
Thank you.
So the next question number 5, what do you expect regarding the environmental monitoring of control atmosphere areas?
Yeah, this one's me.
There.
Yeah, thanks
for
that.
Mark.
This was a really tricky question to try and understand, because we've got two what does the future look like questions here. What does the immediate, i.e. Annex 1 revision going to look like at the end of this year, early next? And I'm pretty confident it's not going to be this year now. There's talk of another revision to the Annex 1. So if we start to think about what does it look like for the future, i.e. what are we going to be doing for environmental monitoring for Pharma 4.0? There's going to be a lot more automation. We're going to be using a lot more robotics for placement of samples and for the taking of samples, and there'll be a lot more gloveless interaction with our devices. There's still a lot of operator interfaces with devices now, and I think as 4.0 comes along, it'll be continuous and it will be predominantly automated. Next. It'll be real time. It'll be multidimensional, and this ties to the contamination control strategy. Not to look at any single piece of information as a unique piece of information, but more holistically as to what is this telling me about control over the environment, and what does that environment have relative to risk. So we'll be starting to apply some artificial intelligence, which will allow for some predictive behavior. If my environment changes by this, my particles in finished product may well change by that. So that's looking at water systems and environmental parameters, bringing them together to give a predictive nature as to what finished product quality might look like. Next. So data quality and the amassing of data quality becomes really critical. And as you can see here, this is a spiral of sorts, because it's never ending. It should be continuously feeding back on itself. Some of them are direct feedbacks, i.e. I look at my data history and I adjust my alert and action limits to give me better and tighter controls. But some of it is following a kappa that then feeds back into the purpose and the method statements that I'm using, the methodologies that I choose to actually take a particular sample. So it's a continuously evolving process. Next. And a single Lego brick, a single piece of data on its own, is really hard to do anything with it unless you're, building a worm, for instance, or a brick was your intended goal. What we really need to do is take all of those pieces of data. And this is the world dream. It was a huge Lego project. There's over 2.5 million bricks, but now we can see what it's meant to look like. We can see what the facility should look like. And this is a really nice analogy as to what individual data bricks can build once you start to look at them cohesively. Next. And so I think we've got a click. Keep going, Bernard, and I'll keep talking. So the summation of data will lead to an understanding, which will give information and knowledge. One more, which is what we're really trying to build. It's this Tetris. We've got to get all of the right little pieces to build up the right way to give us this wall of evidence that shows that we're in control. And that can be, both short-term and far-term future. Annex 1 revision is talking about a control strategy, which is this exactly. And longer term, this should be an impenetrable, quality by design around your environmental monitoring program. I think that's it.
Yeah, that's it. So thank you again. Thank you very much, Mark. So the question number six. So how to monitor and handle documentation in clean rooms that may have minimal impact on final product for class C&D or ISO 7.8 and non-sterile manufacturing. So this question will be answered by Frank.
Yes, it is. This is a very simple answer. Nowadays, there is no there is no reason, no, there is no option that you can believe a clean room is somewhere where you are not expecting cleanliness to be there. That means there is a reason why you have clean rooms of classes C, D, or any other classification. And when you then look into the actual scope of the Annex 1, you see that exactly for this purpose, the Annex 1 is as well applicable. So all the consequences, all the methodologies that I explained earlier, and as well Daniela and Mark, they're exactly the same. Okay, you may end up with your risk assessment in lower frequencies, different methodologies or whatever. Nonetheless, the way how you do it, the way how you handle all of that is exactly the same. Meaning, even for non-sterile products or adjacent rooms that have no direct impact, no direct impact into the contamination, the same principle must apply. The results may be different from the quality risk management, but they need to be documented. You need to know why, and then you can define the methodologies and tasks. So that's a very simple answer, and there is no way out now. You cannot say just it's simple and that's it. Sorry.
I think you already answered this.
This is what I already mentioned. Yes. Sorry, my screen. This is exactly what I was already explaining in the slide. There is a reason why the clean room is classified. Why it is classified clean room C, you know it. Then you need to use contamination control strategy and understanding the process and using a risk assessment, and you can easily do the frequency. I don't think that this was part of the answer. I think there is a mistake in the presentation. That's why I think we can stop here, right here.
Okay.
Yeah. So for the sake of timing, just want to inform you that we already ran out of the scheduling.
Okay, but we are just at the end, so that's good. So thank you for all of the presenters, all of our experts, and thank you for everyone attending this webinars, attending this presentation. So hopefully you have learned something from us today, and so we wish you a good continuation of your day. So thank you
all.
and goodbye.
Thank you. Bye.
Bye.